Swayam Prabha. Digital India. Educated India.
Thank you so much for the opportunity and the invitation, your kind invitation to come, unfortunately virtually, to share with you some of my thoughts around the area of process systems engineering. And it's interesting that I have in my title revolution instead of evolution, because I believe that, yes, process systems engineering evolved towards adapting to the new technologies, but the data is indeed we have experienced a revolution, because we see an explosion in terms of the data. So what I would like to share with you is some of the challenges and opportunities. And as I thought, coming after Rex, I was afraid that I'm not going to be able to cover any new area. I think Rex covered a number of different components in terms of process systems engineering challenges and opportunities, but I hope that I'm going to give a little bit of a different spill in some directions, but also that Rex introduce a number of different subjects that I'm going to cover. So first of all, I do like to dedicate this talk to my former colleague and distinguished member of process systems engineering community, Professor Tunde Goinaki, that we lost at the beginning of this year. And I like to make sure that we're thinking about him and his contributions in the field. Also, I do like to always start by giving thanks and acknowledge the work in my group. This is whatever I'm going to present today is the work of a number of talented young graduate students. I don't know if there are any graduate students in the audience, but this is due to your hard work in the process of obtaining a PhD or a master's degree, or even after as a postdoctoral fellows. So what I'm going to cover today was around two distinguished areas, and I'm going to borrow some examples and case studies for those two distinguished areas. One is around circular economy, and in particular how we can incorporate renewable resources to be able to environmentally friendly design and produce chemicals, fuels, and all of the other goods that makes our life easier. How those things, how we can integrate into our overall supply chain. So as you see, related to the issue of circular economy is also the issues of integrated decision making. Rex talked about the scheduling, planning, and supply chain management. So definitely I'm going to pick on this area to introduce some of the ideas around how we can explore data into the modeling and different analysis tools. And the other area, which again, Rex touched upon, is the area of pharmaceutical manufacturing, and in particular two dimensions. One which is the production of biologics, and the other that it's a production of solid-based drug manufacturing. I am going to use some of the examples that actually Rex emphasized for the production of solid-based drugs. So why are we talking about the data and how we can utilize the data? I thought that I'm going to put this in context of the different evolutions and how this, where we're standing right now compared to what happened in the past. So we see that we are talking about the fourth industrial revolution right now, so Industry 4.0 as we are referring to, and actually some of the people are already talking about the Industry 5.0 revolution. So the first one was basically introducing the mechanical production of goods. The second one introduced the electricity into the mass production. The third one makes the use of electronics and programmable logic controllers into manufacturing. And the fourth one is basically the utilization of cyber physical systems into manufacturing of goods. The fifth one is actually emphasizing how the people will work with those smart machines and robots in order to move the manufacturing into a different level. So, all of those, if we're going to emphasize the Industry 4.0, and again, Rex touched upon all of those different components that made into the Industry 4.0 revolution, that we have sensors, we have both computing infrastructure, but also storage infrastructure. So we're talking about cloud and data lakes, and all of this led to intelligent manufacturing. So now we have smart machines, smart monitoring, smart control, smart scheduling, that all of this generate a large volume of data. And we need to be able to not only store this data, but also be able to utilize these technologies to be able to extract information and utilize this into manufacturing. So we've heard that Rex talked about machine learning, hybrid modeling, the use of high-performance computing, and how we can extract those into knowledge and information. So, of course, it's a process systems engineering conference. We would like to see how process systems engineering can utilize those concepts. What is the role that we have to play in this area? And this is a slide that basically emphasizes how the different agencies and industry embrace this new area. You see that there are different policies, initiatives among the different organizations as well in industry. And I looked at multiple data from the open literature, and I saw that there are, according to a recent McKinsey report, that there are all the different companies embrace the opportunity of incorporating these new developments, the Industry 4.0, making investments, right? So, and piloting some use of those technologies into their production. So they see this as a huge area of development and innovation. The same in academia, we've seen an explosion of publications in the area of Industry 4.0, in the area of how we can utilize big data, but also in the area of machine learning. For those of you that you were at the ACHE meeting in Phoenix, you saw that almost every talk had some flavor of data management or machine learning in it. Of course, this picture gives you kind of a wrong idea of that this technology is easy and you can certainly employ parts of this in the manufacturing currently. And so what I emphasize in this slide is just from our own experience, and this is actually a work that also Rex emphasizes in terms of utilizing these ideas in continuous pharmaceutical manufacturing line. So we had worked with actually Purdue University in a grant from FDA to be able to utilize these technologies and develop the Industry 4.0 infrastructure. And that is not easy with the current technologies. And that's one of the challenges that, again, Rex brought up. Just to give you an idea, for this particular line, for producing solid-based drugs, we had to integrate multiple pieces, and those pieces are not very well talking to each other. So there are different open platform communications software, there are different data historian software, and not to mention that all of this had to be integrated into a platform where you can do a number of advanced modeling and computing calculations, and that's where all the different components are very difficult to organize and develop. So I like to have this on your back of your minds, that actually this is not something that it's very well integrated currently. So that's definitely an area that we would like to be able to contribute as a process systems engineering community. So, of course, my talk today is going to focus on data-based modeling, and this is a contradiction in terms, because always we're using data to do modeling. So always we're trying to emphasize the importance of incorporating data in order to be able to extract information from the process and to include this as part of the modeling. There are different complexities that comes depending on the problem that we have at hand. Supply chain is one example. Pharmaceutical production that I already mentioned is a different example. And sustainability gives a number of different challenges into the forefront. How can we obtain models that predict the output of these complex simulations? How we define feasibility, so we are able to operate in a safe manner, and how to be able to best economically but also environmentally friendly produce those goods. So I'm not advocating that the solution to all of those problems is a data-based modeling, but definitely can be employed to help us understand the complexities around these interesting problems. Again, I'm very glad that I'm coming after Rex, because Rex actually used a different slide, but with the same underlying concept, that with the data-based models, you can see this as a black box, the one that it shows here on the top, that you are getting input, you are getting outputs, and then you're building these surrogate models, and you can use any type of machine learning models to build those algebraic approximations of what the data involved in terms of information, or they're going to be any hybrid structures. And I have here illustrated the serial structure, the parallel or the combined structure, where you can use part of your expertise to build this white box model, like the mechanistic component, and then supplement the information based on what you don't know about the model. And you can do this in many different ways. What I'm advocating here is that many times we don't use data just statically, but you can use data in an adaptive way, and having models that can develop as you are producing more data. And this is going towards this digital twin construct that Rex advocated. So instead of just using a set of data and build a model, we're having this adaptive framework where you can use your simulations or your experiments or your plan to generate data, and you can generate data at areas that you are of much better interest. Like what you see here on the right-hand side is that when you build a feasible space, then you generate data at the boundary of the feasible space rather than overall area. And then your model can also adapt to this. And this is actually an easier way of producing tablets than the one that Rex illustrated with wet granulation. It's a simple direct compaction line where you have the feeders that give the material into the blender, you have the mixing, and then you're producing the tablets. So in each of those unit operations, we are generating data, and what we'd like to do is basically the model running on the background should adapt to generate better knowledge and predictive the behavior of the process as we are moving forwards. And of course, when we are having these capabilities, we can then go ahead and analyze the data and the process behavior by doing sensitivity analysis or feasibility analysis or optimization. So what I'm going to do in the rest of my time with you today is basically going through some of those application areas, and I'm going to utilize different examples from the areas that I showed you at the beginning to be able to illustrate with specific examples what data-based modeling can do in the concept of process systems engineering. So I'm going to walk you through, as you go through the arrows, first in terms of like the predictive modeling, then to the sensitivity analysis, feasibility, to incorporation of uncertainty and optimization. So in the first area of developing models, utilizing the mechanistic understanding of the process, but also data from the experiments, I like to focus on the production of monoclonal antibodies. Where in this case, I mean, we have a very complex process. We have the cells that are responsible for producing the proteins, and those cells are basically grown in an environment that it's the bioreactor. We have media that we have to feed the cells. We have oxygen and air that we have to feed the cells to stay alive. And then those cells are producing different components. With those components, there is also the protein that we would like to produce. So the underlying model should be able to capture not only the behavior of the reactor, that means that the temperature, pH, all of those components that we used in chemical engineering, but also the cell itself. So we should be able to capture the metabolites, the nutrients, and going also another level of complexity, being able to understand how the protein comes to have the final structure, which is the glycan structure, because that affects the quality attributes. So now the product itself has an underlying complexity that we should be able to capture. And the data that we have for this type of processes are at different scales. So we have data in terms of temperature, pH, and the underlying environmental setting. And we have data that, as you see here in the picture on the left-hand side, that are measurements regarding the different metabolic components that are associated with the production of the monoclonal antibodies. So just as an example, and we have worked in this area for quite some time now, this is one of the work of my previous student, Oh Yang, that is currently working with GSK, that went from kriging, which is one form of a Gaussian process, to a dynamic kriging environment, just to be able to capture exactly what I mentioned before, of incorporating not only the static information at one particular time point, but be able to evolve the model as time progresses. And it ended up being that by employing this new dynamic environment, then you are able to better capture the different components that would like to capture in the production of monoclonal antibodies. So what I'm showing here, it's basically the viable cell density plus the production, the titer, the production of the monoclonal antibodies itself. And you see how well the kriging, the dynamic kriging is doing. And I like to just compare with regular kriging, which is just using static information. And this is for a production, for the consumption of glucose, basically the glucose concentration inside the bioreactor. As you see on the top, I mean, we have a better capture of the data, which are the blue dots that it's shown here. Another example comes from the modeling of direct compaction line. And as I mentioned, this is a process that we're producing solid-based drugs, like the tablets that we're consuming for different drugs. And together with the collaboration with Purdue and the ERC Center, starting like almost 20 years ago, we have produced a number of different semi-mechanistic models to describe this individual process. I'm not going to go into the details of that, but there are some underlying equations that basically able to capture the mechanistic understanding of those processes. So again, just to illustrate how the hybrid models can perform better, we incorporate the data that are coming from the process into the mechanistic understanding. Just as an example here, we have done that for the feeding process, for the blending, for the tablet press. And what you see here is, let me have everything here in front of you. You see the original model, and the original model is based just on the mechanistic understanding of the process. And then we start supplementing this by the database components. So what you see as a serial or parallel or combined approach is the different structures that we're using for the hybrid models. And again, you see in all cases, the numbers that it's shown here are basically the errors that are introduced in the models. And in most cases, two different approaches, the artificial neural network support vector regression, that always will see that we have a reduction in terms of the error. And we're expecting that because we are adding more information about what is missing in our own understanding of the process, as very well also Rex mentioned with a number of examples. So moving on, it's important to be able to have models to predict the behavior of the process, but also it's important to be able to see where these models are feasible. So we are able to operate in these areas. So, and of course, I mean, you know, the idea of this, the feasibility analysis is also explored in the pharmaceutical industry. And in the pharmaceutical industry, the idea is basically emphasized with the quality by design initiative and the exploitation of what they call design space. So if you see the definition of the design space that I have here in the middle, is basically the multi-dimensional combination or interaction of input variables that produce products of the right quality. And this is exactly what in our community we are mentioning as a flexibility or a feasibility region. So we explore these ideas together with our pharmaceutical industry collaborations to develop methodologies where you can use not only the actual definition that you see here, the definition that goes back to Ignacio Grossman in the 90s, 80s, that actually can use data to come up with this feasible space. So how you can do that is by exploring some of the ideas of a Gaussian process and incorporating a smart way of adapting the data and generating data at the boundary of the feasible space. So we're using this expected improvement function, which has been changed to accommodate the fact that we don't go towards an optimum solution, but we're going towards the boundary of the feasible space. And then you can explore this and generate more data and then get a better approximation of the feasible space. You can do that in many different case studies. I'm going to illustrate this with the same case study that produce tablets. We have a number of different inputs and outputs in this case. The inputs are the different input parameters is the active pharmaceutical ingredient flow rate and excipient flow rates, but also operating conditions. The outputs are a number of different intermediates and final quality attributes of the final tablet, like the tablet weight, the tablet hardness. So we have a multi-dimensional space that we would like to explore, and we're using the framework that I just illustrated before to generate this design space. So what you see here is that with the use of surrogate-based models, you are able to capture the range of the inputs that gives rise to the products that actually satisfy the quality attributes. And just to, this is not the real tablets that are being produced, but I like to emphasize the fact that the difference between being in the visible space and being outside the visible space. So that means that you have a quality that can pass the inspection and can go out to distribution, and tablets that cannot pass the inspection. So that's the big difference between staying feasible or not. And with the ideas that I just described, you are able to capture this behavior. So moving on to as I said, we're going to move around this circle with the arrows, and the idea of how, of course, we're able to capture uncertainty in these data-based approaches. We know that uncertainty comes from in all of our models, and here I'm just emphasizing one example that now comes from the supply chain management. So in the supply chain management, of course, we've seen work in the literature that are able to capture the different components going from the process to scheduling to planning to supply chain management. And we all have seen that actually the problems that are generated when we have disruptions at the supply chain. So some of the ideas that we have been working lately is to be able to capture these effects by incorporating, by modeling the supply chain as an interconnected graph. And then, as you see with the red on the right-hand side, those red nodes are the disrupted nodes. On top of that, you have uncertainty that comes out of what we usually consider in the process systems engineering area, where we are capturing uncertainty on the demand, on the supplier, or the delivery times. So what you would like to be able to do is basically understanding the interconnections between the disruptions, but also the uncertainty that comes from other different components in the supply chain. So again, moving towards the work that my student Deri Badejo is doing, and actually has presented at the ACHE. He's looking at the supply chain as a interconnected graph, and where basically the nodes are the different suppliers, the facilities, the warehouses, or the customers, and looking at different ways of mitigating the effects of disruptions. How you can do that? By having capacity flexibility, by having multi-sourcing, inventory, alternative inventory. And for the arcs, you see that there are multiple arcs that are connecting the different nodes. And this express the idea that we can have multiple modes of transportation of goods between the different ways that the supply chain is components are connected. So when we're modeling disruptions, basically we are looking at getting those nodes disrupted, but also can be that the arcs are disrupting. So we cannot transport goods from one place to another, which has been exaggerating with the pandemic. And on the other hand, it's operational certainty. As I said, the certainty that comes out of demand and the supply coordination. The solution approach that my student is looking at is basically incorporating these ideas of representation as a graph, but also a rolling horizon approach to address spatial and temporal dynamics. An example comes with 6 suppliers, 4 facilities, 2 warehouses, and 5 customers. This is a 4-tier supply chain problem, as you see, and we compare like deterministic with stochastic models, where we're capturing the disruptions, but also we capture the effects of demand uncertainty. So what very briefly I would like to show you here is the differences in the solutions in terms of the capacity utilization. And if you are interested, I will be happy to send you the one paper that has already been published this year in Industrial Engineering Chemistry Research. As you see, the facility 3 here, illustrated by red, is the disrupted facility. And you see that when you compare deterministic and stochastic solutions, the stochastic solution take advantage of the fact that you have consider this the uncertainty in the facility utilization to be able to increase the capacity on the different facilities in order to accommodate what is coming as a disruption. Same for the warehouse operation. Again, the stochastic is with yellow, the green is deterministic, and we see the capacity utilization increasing. But of course, I mean, with what I'm not showing here, because it's kind of complicated graph, is with an increased cost associated with the stochastic solution. And of course, I mean, there is a trade-off between cost and accepting the risk of not being able to accommodate the customers. So the final part of my talk, and I know I'm coming into the end of my talk, is basically how the data-based approach can accommodate optimization. The first example is the example that builds upon the framework that I illustrated with the feasibility, that we're looking at, again, generating data generating data that are feasible, so you can build a good way of representing the feasible region, but also data that are towards the optimum solution. So what is graphically presented here is a problem where we have an optimum point, the green star that is shown here, and the blue points are the points that are generated at the optimization stage, where the red circles are the points that are generated at the feasibility stage, and those are along the lines of the boundary of the feasibility stage. How you're doing that? Again, I have here a couple of papers that already appear in the literature, but it's basically the adaptation of the generation of points towards the optimum or the feasible boundary. I'm going to use the same example here and also another example, and then I'm going to close my talk. This is again the example of the direct compaction for the production of the final tablets. We have the minimization of cost. The constraints comes out of the simulations, and what we see here is that by optimizing the cost, we are being able to optimize the flow rates for the API and reducing the total cost for production of tablets. But what is more interesting is that we're able also to capture the reduced cost by maintaining process robustness and product quality. The final example comes from the area of sustainability. Since I promised that I'm going to use some of those, all the different areas that we're working on, and how we can, this figure shows that this is a complicated problem. We have experimental data working with our collaborators, and we're trying to build the flow sheet models that produce the final products. We're using literature and historic data, economic data, and this gives rise to a multi-objective optimization with uncertainty, because many of the data that we're utilizing, because we are in the very at the beginning of the development phase, involves uncertainty. So how we can incorporate data generation with a mechanistic understanding of the models to be able to capture the information that is there in the system. So my group is working a lot in this area in the last almost 10 years now. The problem is taking different resources and utilize what we know in the process systems engineering area as a superstructure of alternative technologies. There are a number of different complexities, though. First of all, I mean, the different technologies are not very well developed. We have uncertainty that comes out of the feedstock that creates a number of complexities, but also uncertainty comes out of the prices of both the final products, but the resources that are available. And then you have a number of different technologies that you have to develop, first of all, the different flow sheet models, and then extract the information to be included in the superstructure of alternatives. So again, just to illustrate how this can be done, is all of those boxes that you see in the previous slide. Now it's basically flow sheet models generating in Aspen Plus for the time being, where we then have a set of raw materials, the set of different products, and we're utilizing the different economic analysis and life cycle assessment to get the operating cost, the capacity, the capital cost, but also some environmental matrices like the global warming potential, which is basically represented by CO2 equivalent. So by building first these models, then we can use now these models as our simulations that we can generate data from. So we have both the mechanistic understanding of the processes, but also the generation of the surrogates that represented the different alternatives. We have multiple objectives, and we have already previously discussed this: profit versus global warming potential, and we have uncertainty that comes into the realization of different components like prices, supply, demand, and conversion of the different processes. We use the two-stage stochastic programming with sample average approximation to reduce the number of scenarios in order to calculate the second stage decisions. And I would like to just give you a last couple of slides that basically shows two things. First of all, if you look at the global warming potential on the x-axis and the annual profits on the global warming potential on the y-axis and the annual profit on the x-axis, you see that there are a trade-off between environmental and economic objectives. The second thing that you can see is basically that there is a lot of uncertainty associated with these solutions. So all of this area emphasizes like the 95% confidence interval that the solution that we have generated is actually the optimum solution. We can look also at the solution that is the most environmentally prominent solution, and also the one that is associated with the maximum profit. So if we move from the most environmentally sound solution to the improving the profit, then we are looking at changing now the solution to a smaller capacity, the most profitable products like the extractives from potato peels, in order to, and also the production of hydrogen, because this gives rise to maximum profit designs. So I think I'm running out of time, so I leave you. I'm not going to go through the summary of this. I'd like to have acknowledge the funding sources from NSF, from DOE, and multiple industrial support. I would like to thank you very much for your invitation, your attention, and I wish I was there with you. I would like to, if we have time, to entertain any questions, or at the end I will be here for Rafiq's talk to answer any question at the end. Thank you so much.
Yeah. Thanks, Professor Marianthi, for that interesting talk on data-driven modeling and challenges and some interesting applications. And in the interest of time, we'll restrict it to probably a couple of questions.
Thank you very much, Marianthi, for a very good presentation. It's Togo here from South Africa. I don't know if you can see me where you are.
Yes, I can see you.
Indeed. Yeah, I really appreciate everything that is happening in that space. You really are making a good contribution. One thing that did not come up very clearly in your presentation is the solution times. In discrete modeling, we always contend with the solution time. These problems tend to take very long to solve. I don't know whether you've had this experience and how you're getting around it.
Absolutely, and thank you so much. Because many times, we're presenting our talks and we don't give emphasis how challenging those problems are. I did emphasize the challenges in terms of like the modeling constructs. But it's certainly the computational complexity is another very important component. And Rex actually pointed out that there are some high performance computing, the quantum computing that he mentioned at the end, that it can help us resolving the computational complexity issues, but it's certainly not very easy and readily available. for our computations and for our simulation products. So I don't know if Rafik will gonna talk or touch upon, how the simulation or the simulation software can adapt to the new computational platforms, because definitely I see this as one of the major challenges. And thank you so much for your question. No doubt that those problems are very computational challenging. In order to run a CFD calculation for the bioreactor that I presented, it takes 3 days, and we're not able to capture all the different metabolic components that we'd like to capture. So this is indeed a very important point.
One more question we can handle.
Hi, Professor. Thank you for the very interesting talk. My name is Tanuj, and I'm currently a PhD student at Imperial. One thing which intrigued me a lot was the plot you showed on slide 41, the Pareto curve. I think it had almost a constant region of uncertainty. I mean, it was large, but it was constant everywhere. Can you kindly comment on that? Why do you think that is, and how can we reduce that uncertainty in the solutions that we get?
That's an interesting question, and I'm not sure I know the answer of this, how we can reduce the uncertainty. As you see here from the graph, right? I mean, we are utilizing price data, supply data, conversion and demand uncertainty. So we really put a lot of emphasis of where we're getting our data from. Because especially in the life cycle assessment domain, and if you're using like SIMA Pro as your software to evaluate the global warming potential given inputs and outputs, there is the most commonly used approach to evaluate uncertainty is the pedigree method. And the pedigree method actually is very empirical, is not capturing the price data, is not capturing the supply data. So we went ahead and tried to evaluate, have a better way of evaluating the uncertainty that exists in our simulations. And that's why you see that it's actually, pretty large, the uncertainty range. What you can do to reduce it is basically utilizing additional information, getting more data from experimental, and also, as you're moving towards these technologies becoming more and more developed, then we have a better or at least more certainty in terms of how you can the parameters that are included in your models, like the conversion coefficient, and so on. So I think as we are developing more and more these approaches, I think the uncertainty will be reduced. But other than that, I don't know how you can go about reducing this even further. But that's a very good question.
Thank you, Professor Marianthi. We are running out of time. There's a question from online, from an online thing, but I will actually have it sent it over to you rather than thing, because the next speaker is waiting. I'm sorry about that.
Okay. So let me stop sharing so that Rafik and I will look at this question. Yes. Thank you so much.